So my name is Nichols. Me and some other folks who I'll mention later been working on robot sailboats for quite a few years now. We started a company to do it, so I'm going to talk a little bit about that. But this isn't really about the company, that's just context. What I'm here today to mostly talk about is how you actually teach a robot to sail. But we'll start with the context, which I love computers. Anyways, we're building, I thought I'd change that to, anyways, should be automated, not autonomous, cargo ships powered by the wind and sun. And basically combining the wind and sun with some batteries and regenerative electric propulsion gives us the sort of safety and schedule reliability we need to actually provide cargo services that people will buy.
So just some of the things you made between autonomous and automated is self-sailing
versus somebody's on board. There's a whole lot of stuff, and if you want to talk about it afterwards, I will gladly fill your ear with it. Anyways, so modern weather data and routing models make it possible to actually keep the schedules that customers expect. We're going to start with small vessels, 1 or 2 containers, 30-ish metric tons, serving more remote areas that get very bad service today. And then we'll start with optional crew because that solves a lot of regulatory and technical risk. So why we're building this thing. So first of all, fuel is half or more of the operating cost of your typical conventional cargo ship. It's massive expense. And all the ships in the world together emit something on the order of 1 billion tons of CO2 per year, and they tend to do it by burning very dirty fuel. Automation, sailing, and solar power let us get rid of that expensive and dirty fuel without sacrificing the reliability or anything else. The other thing is, I'm sure you folks mostly probably remember the Ever Given from, I guess that's 2 years ago now. Anyways, the reason ships are getting that big is because if you're burning fuel and you're spending a lot of money to burn fuel, the easiest way to reduce the fuel burn per sort of cargo unit is by making the ship bigger, because you burn less fuel per ton mile or whatever. And that is the why we're building it. And as for who's supporting us, NSF was kind enough to give us a phase 1 SBIR grant. And we also got a little bit of pre-seed money from Deep Future Fund up in Seattle. As for the who, there's me. I got the team together, and one of the co-founders, Jeremy, Dylan, are my other 2 co-founders, and then Heather makes stuff like this certainly prettier than I could. And Graham has done a lot of simulation other work for us, which I'll talk about more later. As for how I got into it, so I grew up sailing on this boat. My parents ran a sail training and research organization when I was a little kid, and we basically bothered humpbacks from Dominican Republic up to Greenland. So how did me and my co-founders get to where we are? So a long time ago, in a Seattle makerspace, well after midnight, we were having a chat, and wouldn't it be cool to sail a robot boat around the world? Because no one had done it at that point. And we played with that for a while, and it's like, okay, we're doing this. This is kind of interesting. What's the, what can we do useful with this thing? That's not just some stunt, right? So data collection is interesting. And you know what? There are a lot of sort of marine protected areas around the world. And, patrolling and protecting those is kind of difficult. So, use a robot sailboat to do that. Now, when we started to sort of look at how to put a company together around this, we realized that there are a lot of autonomous marine data collection companies. The market's not that big in the first place. But at Maker Faire a few years back, when we brought some of our early prototypes, someone came up to us and said, can one of these things carry a few hundred pounds of stuff to Kiribati? which is way out in the middle of the Pacific Ocean, very long way from anywhere, therefore very expensive to get stuff there. And because there aren't very many people, big ships don't call there. So that gave us the idea of cargo. But that brings up the question of why, for thousands of years, just about all sea cargo moved under sail, but it mostly hasn't for the last century. This is actually the last big sailing cargo ship ever launched, 1926. And she, like most ships of her generation, is about as fast as a modern container ship when the wind is with her. However, back in late 19th century, early 20th century, accurate weather data was just not a thing. And the other thing is that handling all those sails takes quite a lot of labor, which meant that a ship like this, although it wasn't burning huge amounts of coal, did have quite a large crew on board. And after World War I, labor rates rose dramatically because the European workforce shrank by about 10 million people, and the only thing that kept them going through the 50s was that back in those days, if you wanted to be like a merchant marine officer, you needed time under sail. So all through 20s, 30s, and 40s, a shrinking number of these guys were sailing, but it was all old men and boys. And there were some fairly bad accidents. But anyways, how does the sailing thing work anyways? So the oldest sails, like this replica Egyptian barge, are pure drag devices, right? It's like holding your hand out of the car window when you're driving down the freeway. Get a force on it, you go downwind. More advanced sailing vessels, like that schooner or the Hawaiian voyaging canoe, the sail forms an airfoil, right? And because you're generating lift as well as drag, you can balance that against the lateral plane area, right? So keels, rudders, things like that, to produce a net force that drives you upwind, right? Which means that you can sail in a lot more directions. Part of the reason I included the voyaging canoe here is because that kind of sail, which is called a crab claw, is actually one of the most aerodynamically efficient rigs that you can build out of just a simple soft sail. But it does take quite a lot of labor. So I mentioned sailing upwind. Let's talk about what that means and probably some terms to do with sailing. So if you're pointed dead upwind, right, case A there, you're not sailing anywhere. And if you're stuck there, it's called being in irons. And if you're trying to go from the wind coming on one side of the boat to the other, and you screw it up, that's where you end up. B is close hauled, which is you're sailing about as close to the wind as you can. C is what's called a beam reach, which is the wind's coming from the side of the boat. And that, for most sailing vessels, the fastest speed under sail is about that point of sail. Then as you turn farther downwind for a broad reach or a run, your sails are functioning more as drag devices than lift devices. And what that means for the speed of the boat, you can see what's called a polar on the left side, where you have the direction the wind is coming into the boat, on the angle, and then the speed that you can actually make is how far out the line is. As you can see, there's a whole no-go zone going upwind, and then downwind, because you're running away from the wind, your maximum speed also goes down. So let's talk about what the forces are. So the first thing that I need to mention for this is what's called apparent wind, which is the wind, if you're standing on the deck of the boat, that's the wind that you feel. That is not the true wind, because the true wind you could think of as the wind that's if you're standing on a rock, that's the wind you feel. So the apparent wind is just that true wind velocity minus the boat velocity, and by vectors. The sail is giving you both lift and drag, which are at some angle to the wind. The forward force drives the boat forward, and then you have that lateral force, which you need to resist with lateral plane if you want to go forward rather than downwind. You also have the hydrodynamic forces. So that lateral plane produces a lateral force to keep you from blowing downwind. And it also, of course, produces drag. So the boat ends up propelled by the vector sum of the aerodynamic forces and the hydrodynamic forces. And if you're sailing at constant speed, it's all balances nicely. However, there's a little bit of a problem, which is that your aerodynamic forces are, at the center of effort of your rig, which is up over your head, and the hydrodynamic forces are at the center of effort of your, keel, rudder, etc., which is under your feet, right? Which means you get this big overturning moment that wants to roll the boat over. And boats resist that by some combination of where the center of gravity is and the shape of the hull. So sometimes you want to go somewhere that is upwind of you and that is within that cone of that no-go cone. So what you do for that is called tacking, which is you switch the direction that the wind is coming into the boat from side to side by turning through the wind. And if you do a number of these tacks to go upwind, it's called beating to windward. For us as a cargo vessel, who has to keep a schedule, how fast we can do this in terms of velocity made good to windward is a key part of, what sort of times we can actually schedule. Now, if you looked at the picture that I had earlier, you notice that the sails we have don't look much like conventional sails. That's because they're actually hard wings. Now, we chose those for a bunch of reasons, but probably the most important ones is they're more aerodynamically efficient. And the other is that they're way easier to control than a soft sail. That's because a soft sail has all sorts of weird and non-obvious boundary conditions between where it does something useful for you and when it just flops around uselessly, destroying itself. So that's actually somewhat hard to detect with a computer, especially since the way it's done if you're sailing a physical boat by hand is that you look at the sail, right? And that gives you a sort of difficult sensor problem if you want a computer to be able to do it. It's not impossible, but wing sails are better other ways. Wing sails also give us a place to mount a huge number of solar panels. Flexible solar panels are a thing, so we can just skin it. So that's enough of that. Let me talk about actual boats that we've built. Starting with our Pathfinder prototype, it's only about 5 feet long. I can pick it up. Basically, we did this as the smallest, cheapest boat that brought sort of our key things together, and how fast can we get it working. The compute for it was, or the software stack was something called ArduPilot, which started life as a quadcopter control, open source quadcopter control software. But someone wrote some sailboat modules for it, which meant that we could just, plug it in and get going. And I had some BeagleBone Blues from sort of earlier iterations. BeagleBone Blue is nice because you have compute and an IMU and some other nice sensors on it. Final form of it is like what we have here, which we have trailing edge flaps. And then the wind vanes on top are wired into the feedback of off-the-shelf little RC servos. So you just, say, go to this angle, and it holds that angle to the wind, more or less. So first time we sailed that was about April of 2021. We sailed it a whole bunch in both Lake Washington and Green Lake. We're based in Seattle. And we really did, get a lot of sailing in with it. Some of these pictures are from Green Lake. Some of them are from Lake Washington. And, it's a small boat, so it is not a fast boat. And the hulls are basically just boxes with pointed ends. So, it's there as a proof of concept. It's not there to, to be a huge performer. We also found that there was a terrible problem with ArduPilot that we never actually managed to solve, which is that some combination of ArduPilot and our setup, when it was sailing to waypoints, would hit the first waypoint, go a ways to the second, and then just completely lose the plot and wander off. And we found a lot of things that weren't causing this. And we also discovered another bug in ArduPilot sailing code, which was the capsize protection didn't fire until about twice the roll angle it was supposed to, which was well past the point of no return. Anyways, so after that capsize, we decided that we didn't want to use ArduPilot long-term anyways for a variety of reasons, and we'd rather use PX4, which is from the same, also open source quadcopter control code. However, it has a remote console, it has modular software architecture, it has a whole bunch of things that are just better. So we rebuilt our control box around a PX4 and a Raspberry Pi 0W. We added cellular data, we added much bigger batteries, and a bunch of other stuff that made the boat a lot better. So that meant that I had to actually write some sailing algorithms and not just hack on something that somebody else had written. So conceptually, it's controlling a wing sail is pretty simple because you command the angle of attack. Because the way we had it set up, you just command an angle of attack, which is and if you're in sort of the lifting regime, so on a reach or close hauled, you want that under the angle of attack that the wings stall at. If you're going downwind, you'd like to set it so it's a great big wall that the air pushes on. The other fun thing is for a sailboat, you can actually, if you have more than one sail, you can use the sails to steer the boat. And you can do this with just about any sailboat that has at least two sails. For a soft sailboat, this is generally a pretty expert evolution if you want to do more than just trim the boat to maybe sail a little faster. For a wing sailboat, it's actually pretty simple because we can just set different angles of attack for the foresail and the mizzen, and they'll produce a turning torque on the boat. This turns out for us to be really key to make the boat actually able to tack, because if you leave the angle of attack where it is, when you try to tack the boat, it will just stop. And it won't do anything, because as you come up into the wind, suddenly you have a large aft pointing force vector. So you at least have to feather them. And our boats don't have a lot of inertia. So you need the sails to actually push it all the way around for the tack. The other thing is wind attack, right? Especially if you're sailing between waypoints. Now, the way we have done it for the boat, for what we've actually sailed, is by cross-track error, right? So you let the cross-track error, which is the distance from between the boat and the track between the waypoints you're going back and forth between. As soon as it reaches some limit, you tack back. And this is great for confined waters because the boat's going to be in this rectangle, right? And you can check whether that rectangle includes a rock very easily. It's, however, a little less efficient than it could be. What we've done a little bit of work on for for more open waters is by looking at the best velocity made good towards the waypoint you're going towards, right? It's probably more efficient. However, you should probably only do it in open water because you're going to wander all over the map. It also means that you have to have really good data on vessel performance in order to get a good result, because you have to know, is tacking, minus whatever the cost of tacking is, going to actually get me a better velocity made good. If the data I have on that isn't good, well, I'm not going to make a good decision there. So March of last year, we actually got that SBIR that I mentioned. And the first thing I did with the first federal grant that I was ever personally responsible for as PI was I took a bunch of it out in cash, and I drove down to Oregon, south of here, and I handed a stack of Benjamins to a sketchy dude in a muddy field to buy a 50-year-old and therefore very inexpensive Hobie cat. Amazingly, the trailer lasted long enough to get it home. When we finally actually got some space, however, I was driving it down from my buddy's house, from Dylan's house, where it had been parked most of the time since I bought it. And the trailer tongue just snapped. Luckily we had a chase car who Heather was driving. She just leaned on the horn. So we stopped, and luckily there were some very nice people who let us roll it into their driveway, and gave us a bunch of self-tapping screws and stuff. So we put a plate back on it, which got it the last 5 blocks to our new shop, where it promptly broke again. And we ended up building a new trailer because obviously the one it came with was way past salvage. So we took off the rig that it came with and all that, and we started putting together our wing sails, putting together the electronics. You can see early test getting it up in our little parking lot. Then we have the battery box, the battery charger. We have our power distribution box. Now, probably the most useful thing here is you see there's sort of a black lump up in the upper right corner of that picture. That's the power relay. So all of the actuators and everything else, a robot this big, the actuators can actually do quite a bit of damage to themselves, to anyone who happens to be in the way, and so on. So we ran the power for all of them through that big thing, and then we ran the coil power for it through our e-stop switches. So if you smack the e-stop switch, it cuts the power to the actuators. So the actuators can no longer make it worse. Whatever the problem that caused you to hit the e-stop is. We also have the brain box here, which has Raspberry Pi, a PixHawk running that PX4 firmware. The PixHawk also gets us the IMU and the GPS processing and a bunch of other useful stuff like that. We've got a little Daisy AIS receiver, which I think is sold on Tindy these days. And power distribution and fun stuff like that. So once we had it together, we could actually start taking it to the water. Our original idea, so I want to talk about how we mounted the sails. So the sail spindles are basically, the Hobie Cat has, on each hull, has sort of a stanchion coming up, and a big corner casting that holds the whole frame, that holds it together. So we just drilled holes through the tops of 2 of the corner castings and dropped the masts in. Now, the way we originally did it was we'll just, lever the whole, 20-foot tall sail with, a bunch of area up with guy lines, and then it'll just drop in, and this will be easy. It didn't work that way. It was actually quite terrifying when we tried to do it that way. So we added a hinge, which meant that we weren't doing that anymore. And the sails came up quite nicely, and then we were able to actually take them out and go sailing. We started with pretty mild winds because we weren't quite sure how it would behave in heavier winds. The first time we took it out, though, it was raining, and it was 7th of January this year, so it was also bitterly cold. That's why we're all wearing the weird orange jumpsuits, those are exposure suits. It turns a midwinter dip in Puget Sound from life-threatening to merely embarrassing. So I want to talk a little bit about what we actually did with the software and hardware stack. And this ends up pretty dense because there's a bunch of stuff going on. As I said, we have that main computer running ROS2, Pixhawk running PX4, and a bunch of other little bits and bobs. We have a 4G to Ethernet router because that lets us, instead of having to connect to the vessel directly, we can control it basically. It calls up to a AWS instance in the cloud, and Q ground control software running on a tablet calls the same instance and lets them talk to each other. Made life a lot easier. The sails also ended up each with a Raspberry Pi running ROS2 to actually do all their controls. These 3 boxes are the inside of one of the wings. We ended up using knockoff Pelican cases because it's the cheapest waterproof case that latches and without tools. That's the other thing. When you're doing development, you will be in and out of your electronics all the time. Once we got it sailing a little bit, we added a couple of solar panels to the wings to test that. That middle picture, I think, is one of my favorite pictures of the original configuration because it's just taken from such a perfect angle by one of our friends. That was actually a little bit sketchy because you can see the back of that boat there. The guy who took this is standing on top of a wall. So I couldn't see that boat until we were almost on top of it. And just before this, I've taken a very sharp right turn to avoid hitting it. Because that would have been troublesome. We probably wouldn't have done it any damage, but it might have damaged us, and there would have been paperwork. We actually did some simulation work as well. This is an overhead picture of where we did most of our testing, Shoal Bay Marina in Seattle. And that T-dock is where that picture was taken from. So we were able to refine this simulation to where we could pretty closely replicate actual trips that we did. So therefore, we think it is probably a pretty good representation, at least for low wind speeds. Now, one of the things about the configuration of the boat that I've showed you is that we had to put the sails up while it was still on land and then roll it down the ramp into the water, which, if the wind is blowing 6, 7, 8 knots, isn't too bad. However, if the wind is a lot higher, it can be troublesome, as we found out when we started trying to expand our envelope. Because, you remember what I said about corner castings? So they're cast aluminum. They probably weren't great to begin with. By the time this happened, they were about 50 years old. And we drilled a big hole in the top of each one. So when we had it tied to the dock in about 16 knots of wind, we broke the corner castings. And then pretty much immediately rebuilt it with much heftier cross beams. That's like a 2-inch by 6-inch rectangular aluminum tube with like, I think it's 1/8-inch ball. So it's much stiffer. Basically, we took the same thing that we'd been doing, putting a spindle down into the top of each of the stanchions in the hulls and bolted them to our big cross beams. And then you can sort of see it, but it's a little hard to see. We have cross cables, or we have a pair of cable X's with the middle part driven apart, which makes this very, very torsionally stiff. We moved all the electronics boxes around from where they had been. And we've actually taken this sailing once, but we didn't have anyone take pictures of it on the shore. So I don't have any pictures of that, sadly. Anyways, so I put together a couple of slides of most of the software we used, some books that I've personally found hugely influential. All the really good diagrams in this were copied out of Aerohydrodynamics of Sailing. The middling ones I copied from Wikipedia, and the shitty ones are the ones I drew. C.A. Marquez, super interesting guy if you're interested in sailing at all. I put the Bolger and Smith books at the bottom because they sort of levered me out of the idea of what a sailing boat had to look like. And this is a bunch of software. Some of this I wrote. A couple of these modules are ones I wrote. The driver stuff, and then the rest is stuff that we were able to bring in for that. Anyone who wants to take a picture of this, get some of those links. Anyways, so here's some of the hardware we used. So some of the, I think, more unusual hardware. And the resources, Tom Spears, has a whole website about wing sails. Amateur Yacht Research Society is like the home for all the weird boats. And Eric Sponberg has done a lot of interesting stuff on unstayed rigs. So, any questions? Yes, Josh. Actually, let me bring you a microphone so people at home can hear you.
Okay, so I saw that there are solar panels involved. And you mentioned that you had a 100-watt panel, and so I'm curious, what was your power budget, and how much of the time were you above it and below it, and how much time did you actually capture the 100 watts worth?
So,
Do you need the microphone back?
No, I have one right here. So the solar panels are there to test that we were getting solar off the wings, right? They were not there to power the boat. Our actual operations, we were, doing day-long tests, right? And it's got more than enough battery power to do that. I think the farthest we ever drained it on a test day, 200 amp hours of 12-volt battery, was we took it down to about 60%.
What was your total power budget?
That depends on whether we had auxiliary propulsion on. With auxiliary propulsion, we were pulling about 45 amps off the battery. With just the wing sails, we were averaging more like 5.
Cool, thanks.
Yeah.
Yeah, so on the early prototype, you mentioned using servos as the mechanism that turned the sails.
Yeah.
What is it on the current ituration?
There's a big motor in the that's actually in that circular main spar, and that's driving the sail angle.
And it's continuous power to the motor?
Yes.
Okay. And I'm assuming that power goes up depending on the amount of angle
Yes.
required. Yeah. Okay.
Yes. It goes up in higher wind. It goes up if we're trying to hold a higher angle of attack. So it's actually a little higher if we're going downwind.
Thanks.
Are there other sensors in the sail monitoring like how much strain or torque is on the sail as you move?
Whoa, can you repeat the question into the?
Are there other sensors on the mast for things like strain or torque on the mast to give you a sense of how much push they're generating?
So the only one that sensors that we're using that are actually mounted on the sail are the wind angle, angle of attack basically, and the angle of the sail to the boat. We haven't gotten to the point where we're doing the full strain gauge instrumentation. We're judging how much power we're generating by basically how fast the boat goes. And right next to you.
Just two quick ones. Could you elaborate a bit on how the trailing edge adjustment works on the sail?
So it's just like the flap on a wing.
Yeah.
Right. So if that trailing edge flap is fared to the rest of the wing, that's sort of the minimum amount of force you can generate. And then you deflect it, and there's a slot between the main element and the flap. So it's just like a slotted flap on an airplane wing. It increases the amount of lift you can generate, and also increases the drag.
And that's pivoting on the trailing edge of the solid wing.
Yeah, the pivot's actually a little forward of the trailing edge. That ends up being one of the way too many optimization knobs you have to twist.
And just out of curiosity, on the broader agenda, what do you expect the piracy issues are going to be with a boat out there all by itself?
So here's the funny thing about piracy. Piracy is basically a strong arm crime. It's like knocking over a liquor store on a larger scale, right? Some guys board the target vessel, point a gun at the captain, says, "Do what I want," right? Or "Do what I say." That doesn't really work with a computer, right? There's no one on board to threaten.
No, but I can just tell you what.
So boarding an uncooperative vessel at sea is incredibly difficult, right? If the vessel knows you're there and is maneuvering to avoid being boarded, it's basically impossible to do without a helicopter. So, and nice thing about the sensors that you need for automating a vessel like that is you have really good situational awareness. It's basically impossible to sneak up on. And if there's always human supervision. Even when we go to full autonomy, there's always going to be human supervision on shore, and it's like, there's someone, someone's trying to get really close, or someone's very close. A remote human needs to deal with this situation. And again, someone boards if they actually manage to board the vessel, there's a lockdown computer system. It's got a lot of propulsive power, right? Like, it's perfectly capable of breaking a tow line. I think once we have full autonomy, it will be almost impossible to hijack one on the open ocean. And doing so is basically the same problem as hijacking it remotely, right? It's a computer security problem. And current pirates, it's not a bunch of hackers. It's a bunch of guys who knock over liquor stores on a giant scale. Does that answer the question? Yeah. Can you pass the microphone forward?
Can you comment on the legalities and permitting required for doing something like this?
That is a huge thing. So the reason that we're starting off with crew on board is because that puts us squarely in the existing regulatory space, right? As far as the Coast Guard is concerned, we're a weird sailboat. There are rules for sailboats. One of the other reasons we're starting with such small vessels is we're under 100 gross tons. And there's a big regulatory step change for any ship at 100 gross tons. So under that, the regulations are pretty simple. Once you go beyond that, you have to get a classification society involved, which is not a bad thing. Or actually, not just if you go over 100 tons. If you want to carry hazardous cargo, you also have to become what is called an inspected vessel in Coast Guard, the way the U.S. Coast Guard handles it, which means that you have to get a classification society like ABS involved at the design phase. None of the restrictions there are either unusual or even all that difficult to meet. They cost some money and they take some time. Full autonomy, the regulations are not there yet, right? And it is, at least in theory, possible to get the local Coast Guard office to sign off on it anyways. But that's an awful, but did the local commandant get up on the wrong side of the bed today? He is a hell of a risk to take. The Coast Guard is working on it. Coast Guard publishes a magazine like 3 times a year called Proceedings. And last summer they did a whole issue on ocean autonomy. And it's pretty clear that their head is in the right place, but the Coast Guard doesn't do anything. It doesn't make regulations quickly. So eventually there'll be regulations. I think they'll probably make sense, but they're not there yet.